Hi, welcome to Calculus. Today we are looking at section 9.1. We're going to look at sequences. Sequences are going to set us up to do infinite series here starting in section 2. So these are important. A lot of it will look familiar, I hope, but let's get started. A sequence is just a list of numbers in a given order. So a sub 1, a sub 2, a sub 3, out forever. So we are looking at infinite sequences here, numbers that go on forever. The little numbers along the bottom are just called the indices. Um, and so one possible sequence would be the sequence a sub n. Notice we put in braces. That's just defined to be 2, 4, 6 out forever, where the nth term is 2n. The other way we could write that is in these braces, we could put the rule 2n when n goes from 1 to infinity. And so that would supply us with all those terms as well. And it's important to note that the index can start at any number whatsoever. So we're going to talk about convergence and divergence of these sequences as well while I move my computer so you can see the rest of the board. There we go. So a sequence converges to a number L if you take the limit of those terms and it goes to L as n goes to infinity. Very much the definition that we would have used for a limit at infinity back when we learned limits. And the sequence a sub n diverges to plus or minus infinity if that limit is plus or minus infinity. But does every sequence either converge to a number or diverge to plus or minus infinity? And that's a good question. And the answer is no, and here's an example. Here is the sequence a sub n where the terms in the sequence are just alternating 1 and negative 1. Well, it does not converge. If you took the limit of these, you wouldn't be able to get it to shrink down onto just one number. The alternating bit just kills that. But it also doesn't go to plus or minus infinity, right? It's just going between 1 and negative 1, so it's clearly, the limit here is not any sort of infinite. So we have all sorts of things that can happen. We can have them converge to a number, we can have them be divergent where they just go off to infinity, or we can have something like this one where it diverges but it doesn't go to infinite. So let me rewrite my board and let's continue. All right, so continuing on, we have some limit rules for these sequences. They will look very similar to limit rules we had when we learned about limits. So let's say we have the limit as n goes to infinity of a sub n is a, and for b sub n it's b. The limit as n goes to infinity then of a sub n plus or minus b sub n is just a plus or minus b. If you do a constant multiple of your sequence, you just get a constant multiple of the limit. If you multiply your two sequences together, you get you multiply the limits. And if you divide the two sequences, you divide the limits. So it works out really very nice. So basically, we can treat these limits very much like we did our regular limits when we started calculus. So for instance, if I want to take the limits n goes to infinity of this thing, 4 minus 7 times n to the 6th over n to the 6th plus 3. The trick on these was to divide everything by the highest power of n. So when I do that, I get 4 over n to the 6th minus 7 over 1 plus 3 over n to the 6th. And anything where the denominator is going to infinity is going to go to 0. So we can kind of sort of just, we're not really plugging in infinity, but we're accepting the fact that these two pieces go to 0. And so we get 0 minus 7 over 1 plus 0, and that is negative 7. All right, let's move the computer. All right, then we have what's called the sandwich theorem. It says if you have three sequences, A, B, and C, and you have a number n such that if you get out far enough in your sequences, so you are looking at terms of your sequence that are indexed higher than that n, and then if we have that the limits of A and C as n goes to infinity are both L. Because of the sandwiching here on B, its limit also has to be L. If you go far enough out into those ends, then it works. And then the continuous function theorem. This is just another extension of all these things that we've already been saying, that we can treat these very much like we did regular limits. It says if a sub n goes to L and f is a function that is continuous at L and defined for all the a sub n. So basically, you just want a function you can plug stuff into, and that is continuous. Then f of a sub n is going to have approach f of L. So I want to show that the limit of this sequence, n plus 1 over n to the third, is actually 1. So to do that, I said, okay, well, let's start by defining a function here to be x cubed. We know that x cubed is a continuous function everywhere, so it's not going to have any problems with plugging in any of these sequence values, and it's going to have a limit just fine. So now I just evaluate the limit on the inside, and I use the same trick I did just a minute ago. I divide by the highest powers of n. So when I do that, my limit as n goes to infinity becomes 1 plus 1 over n over 1. I'm dividing by those n's. And since 1 over n goes to 0, we just get 1 over 1, which is 1. And so then by the continuous function theorem, the one I want, I just have to plug in that limit into my function. And so f of 1 is 1. And we showed that our sequence has the limit that we hoped it did. All right, let's get some more on the board. All right, continuing on. One more theorem just to kind of nail down what we've been saying. Basically, we can treat the limits of our sequences just like we would any regular function, even though our sequences are most assuredly not continuous functions. Suppose f of x is a function and that a sub n is a sequence such that a sub n is equal to f of n. So we have a function that spits out all these values of the sequence, but it's actually a function and presumably takes on other values as well. Then the limit as x goes to infinity of f of x being equal to L implies that the limit as n goes to infinity of a sub n is also equal to L. So basically the sequence traces along the function and pops in every integer. All right, so to do this, so a problem here I want to find this limit. You can see I already put it 0. The limit as n goes to infinity of n squared over e to the n. So I just defined my function f of x to be x squared over e to the x, and now I'm evaluating its limit as x goes to infinity. To do that, I'm using L'Hopital's rule. I'm going to have to do it twice, because these are both infinite pieces. So I take the derivative of the top and the derivative of the bottom. That gives me the limit as x goes to infinity of 2x over e to the x, still infinity over infinity. But if I do it one more time, I get the limit of 2 over e to the x. That's no longer infinite. We're taking and we're dividing by something that's infinite, so we get a limit that is 0. And so last thing, or no, not the last thing. I still have a whole nother page of notes. Last thing on this board, I have a theorem that gives us a few kind of interesting limits. The limit of the natural log of n over n is 0 as n goes to infinity. The limit of the nth root of n as n goes to infinity is 1. The limit as n goes to infinity of x to the 1 over n is 1 as long as x is positive. The limit as n goes to infinity of x to the n is 0 if the absolute value of x is less than 1. The limit as n goes to infinity of 1 plus x over n to the n is e to the x. That's fun. And the limit as n goes to infinity of x to the n over n factorial is 0. And in case you're not familiar, n factorial is just n times n minus 1 times n minus 2. Basically, multiply all the numbers all the way down to 1. All right, so there we go. Let's get a little bit more on this board and finish this section up. All right, so continuing on with our talk about sequences, recursive definitions. You need two things. You need the value of the initial term or possibly more than one term, so terms. And you need a rule for calculating any later term from the preceding terms. So for example, the Fibonacci sequence, 1, 1, 2, 3, 5, 8, 13, and it keeps going. What you need to be able to generate the Fibonacci sequence is to know that the first term is 1, and you need to know that the second term is 1. In this case, we need to know 2 terms. Because the rule for the nth term is that you add a sub n minus 1 and a sub n minus 2. So you add the 2 preceding terms. If you want the 5th term, you add the 4th and the 3rd. And sure enough, that will generate your Fibonacci sequence. So then we can talk about sequences being bounded. A sequence is bounded above if there exists an M such that A sub n is less than or equal to M. It's bounded below. Same thing, if there exists an M such that now A sub n is greater than or equal to M. So your sequence is always smaller than that number or it's always bigger than that number. And it's just considered to be bounded if it is both of those, both bounded from above and below. And so then we can also talk about increasing and decreasing, or I'm sorry, non-increasing. I can talk. This is going to work, really. We have a non-decreasing sequence if each successive term is greater than or equal to the one that came before it. So in this case, a sub n plus 1 is bigger than or equal to a sub n. It's non-decreasing if each term is smaller than the one that came before it, or smaller than or equal to. And it's monotonic if it's either of those things. So if the sequence either only gets bigger or it only gets smaller, it is considered to be monotonic. And from that, then we have a theorem. If the sequence a sub n is both bounded and monotonic, it has to converge. Okay, if you have a bound on it, so it never gets bigger than, say, 5. If your sequence never gets bigger than 5, and it's only going in one direction, well, so it's bounded, so it's never getting bigger than 5, and it's never getting smaller than something else. But it also has to be monotonic. If it's bounded and only going in one direction, it will converge. So there you go. Those are sequences. Thanks for watching.